So now let's look at part 2 of this question, which is asking us to solve the Helmholtz equation on a disk of radius r. So there's the disk, r is the radial distance out from the origin, that's theta, so that's the line theta equals 0, which is entirely arbitrary. I could rotate this disk through whichever angle I like, counterclockwise or clockwise, it doesn't make any difference. We're still analysing the same pattern, so this is in some sense an arbitrary choice where theta equals 0 is. The radius is a, so this edge of the disk is at r equals a, and Helmholtz's equation here is 1 over r d by dr of r d phi by dr plus 1 over r squared d2 phi by d theta squared plus k squared phi is equal to 0. And we're told that the solution is bounded at r equals 0 and it satisfies a boundary condition at r equals a, which we're asked to do in part A. So what's the boundary condition? Well, it should be that the normal derivative of phi is equal to 0 at r equals a. So there's the normal to the boundary. That's a directional derivative. N dot grad phi is going to be 0 at r equals a. Well, the normal direction is clearly in the direction which r is increasing. This angle here is 90 degrees, so the normal is in the r direction. So this derivative should be in the r direction. So i.e. d phi by dr equals 0 at r equals a. And what does it satisfy? What's its physical interpretation? Well, that's that the chemical cannot flow out of the domain and we have a closed system. So the chemical cannot leave the disk at r equals a, so we have a closed system. Okay, now part B, we're told to assume that phi is sine m theta times f of r. State giving a reason or restriction on m. Well, m's going to have to be an integer. So phi has got to be a periodic function of theta with period 2 pi. So what's the reason for that? Well, if we look at the disk here, if I choose any point in the disk, let's just choose a point here for the sake of argument, then phi takes a certain value there, and the pattern is determined by the value phi takes. Well, in particular, it's sine. If we go all the way around through an angle 2 pi, when we get back to where we started, phi must take exactly the same value, because all that's happened is we've come back to the same point again. So phi's got to be periodic with period 2 pi. Well, that's only going to happen if m is an integer. So phi must be periodic with period 2 pi, so that requires m to be an integer. And perhaps to illustrate that, if that's not clear, supposing we take a counterexample. Supposing I sketch sine of x over 1.1, let's say. Then what does sine look like? Well, here's 2 pi over 1.1, slightly less than 2 pi, and there's 2 pi. So sine of x over 1.1 will do something like this. It comes back and repeats itself when you get to 2 pi over 1.1. This is x here, and then it carries on. So when you get to 2 pi, this point here is not the same as the point you started at the origin. So in this case, if I look at that point there, theta equals 0, or equally theta equals 2 pi describes that point. But on this sketch here, theta equals 0 has got this function being 0, and theta equals 2 pi has got a different value. So these things are only going to equal each other if this is an integer that's pre-multiplying x. Right, derive an ordinary differential equation for f. So that's what we want to do next, an ODE for f of r. So we want to take this form for phi and substitute it into Helmholtz's equation up here. So let's do that. Right, so let's do the first term. Well, the sine m theta, these derivatives are on r, so we can take the sine m theta out the front. So I have sine m theta divided by r coming out the front. Then d by dr of r times f of r remaining in that term. Then here I've got to differentiate phi twice with respect to theta. Well, if you differentiate sine m theta once with respect to theta, you get m times cos m theta. Do it again, you'll get minus m squared times sine m theta. So here we're going to get minus m squared times sine of m theta times f of r divided by r squared, then plus k squared phi, so plus k squared sine m theta times f of r is equal to 0. Now my sine m theta we can divide through by that. So if sine is 0, of course this equation is just trivially satisfied. You get 0 equals 0. And if it's not, we can divide through by it. And what we're left with then, if we expand this bracket out here, I've got 1 over r, differentiate this product, you get r f dash plus f times the derivative of r with respect to r, which is 1, minus m squared f over r squared plus k squared f is equal to 0. Let's expand this square bracket here. So that's f dash plus, so I lost a derivative here. Yes, I have, haven't I? That one there, that should have been an f prime. So when I wrote this down, it should have been d by dr of r times f prime, because there's another derivative there, making that f double dash and that f dash. So then I've got f double dash here plus f dash over r plus k squared minus m squared over r squared times f is equal to 0. Let's multiply through by r squared, because then we'll get a familiar equation, r squared f double dash plus rf dash plus k squared r squared minus m squared f is equal to 0. And we're not asked to identify it. For what it's worth, this is Bessel's equation of order m. And we saw this in the lectures of order 0, I think. And we're told don't attempt to solve it, but there's the ODE. Right, so then, assuming that the solution for f does not change sign over the disk, sketch the expected pattern when m equals 2. So now let's set m equals 2. So that means then that phi is sine of 2 theta times f of r. Well, if f doesn't change sign, as we're told, then we can exclude that from consideration. We're interested in when phi changes sign. And let's do what we did in the lectures, which I think we decided if phi was greater than 0, then that's white. And if phi is less than 0, then it's black. It doesn't really matter which way round you do this, as long as you state clearly what you're doing. F doesn't change sign, so we really only need to worry about when sine 2 theta changes sign. So let's sketch sine 2 theta against theta. Well, okay, by the time we get to pi, then sine 2 theta, the argument is 2 times pi, so sine has completed a whole cycle by the time you get to pi, so it must look like that. And then again, the same, like that. So we get 2 periods of a sine wave between 0 and 2 pi for sine 2 theta. So the pattern then, assuming that k is in the unstable range and the thing is spatially unstable for Turing instability, then what pattern are we going to see? Well, what's this angle here is pi over 2, this one here is 3 pi over 2. So phi is positive between 0 and pi over 2, so here's theta equals 0. There's theta equals pi over 2. Over here is theta equals pi. Down here, theta equals 3 pi over 2. So in this sector here, theta is between 0 and pi over 2, which is this range here. So phi is positive, so that's white. So this bit's white, so we'll leave it. And then in this sector, theta is between pi over 2 and pi, so that's now in here. Between pi over 2 and pi, phi is negative, because sine 2 theta is negative, and f is not changing sign at all, irrespective of what value of r we take. So if phi is negative, that's black, so we can shade in this whole region. And the whole region gets shaded because as you vary r from the origin 0 out to the edge at r equals a, nothing changes because f keeps the same sign, as we're told in the question. Then when theta is between pi and 3 pi over 2, that's here, phi is positive, so that's white, and then this last sector is black.